Morning everyone. Today's session is polymerase chain reaction, abbreviated as PCR, also called a thermocycling reaction. So what is PCR is, if you take a eukaryotic cell, the nucleus, the DNA content, just before it's divided into the two daughter cells, the chromatin material gets divided into two to be shared equally to two daughter cells. During the S phase, this takes place in the in vivo conditions, within the live conditions. But what about the in vitro conditions now? If you maintain the same temperature, same parameters, is it likely to happen in the in vitro condition as well? This very idea was got by Karimulis, and he came up with an idea of PCR, and he was successful in that, and he was awarded the Nobel Prize in the year 1993. Before exactly going to the mechanism of PCR, we'll see there are some requirements for PCR reaction. What we call as the raw materials. What are the raw materials required for the PCR reaction? The first one is the template DNA. It's a very important one, like where I need to amplify my gene. Second one is the DNTPs. The nucleotides like A, G, C, T base, where they need to incorporate the new strand or the growing strand, and the magnesium chloride and salts and the buffer to maintain the pH of the conditions to make it lively. And then the Taq polymerase or the DNA polymerase, which is very much important to add the DNTPs into the strand. The last one, the foremost important one, is the primers. Primers actually very crucial in this case. Designing a primer is very important as well. Say, for example, if you take a gene, for example, insulin, and insulin codes for this mRNA, insulin mRNA, which then moves into cytoplasm for translation. Within the cytoplasm, translation takes place. The polypeptide chain undergoes conformational changes and forms a functional insulin molecule. But this is what exactly the requirements for the thing. Now, what are primers? Primers are just a sort of oligonucleotides which need to be designed manually. But there are some ideal conditions for the primers. The first one is it should be an oligonucleotide, approximately 18 to 25 base pairs, not be less than 18 and not more than 25 base pairs. And the next, it should have an annealing temperature, right? Annealing temperature in the sense like the primer need to go and bind to its complementary strand, that is called annealing temperature, where it gets annealed there, like that should be around this condition. And this again varies different reactions, right? It depends on the primer also. And the G plus C content should be 50 to 60%. This is very important over here because like G and C bonds with the triple hydrogen bonds and A and T bonds with the double hydrogen bond. So to break up the bond between G and C, more energy is required than like with the A and T. So that's the reason why G plus C contains more, is a predominant position. Like the annealing will be very strong in this case. And the same 3' end of the primers should always end with a G or a C. This is again in accordance with the third point, that the G plus C is 60. So the more, as mentioned, like why should it a 3' end should be a G or a C, is like to prevent the breathing on the ends now, right? Say for example, if I'm designing a primer to a template strand G, C, T, A, T, C, it's just an example now. And the 3' end is having a G band over. Now the G bond with the C over there, and the triple bond exists over there, right? So it's a very strong bond. In other instance, like if I take A, C, T, A, and say for example, and 3' end if it's A, now this A actually bonds with the T and is again double bond. So the bond between the G and C is stronger than between A and T. So in that case, the A might not combine with that. So it might just breathe it off, like that's what. And then the 3' end of the primers, both the fibers, the forward primer as well as the reverse primer, and they should not be complementary. The very reason behind this is also very simple here. Like if, for example, you take it's like G, C, C, T, A, G, C, A, T, A, G, C. And this is a forward primer. And now this is a reverse primer. I'm designing in the opposite way. Just for example, instead I'm giving this. And now this is my reverse primer. Now if you can see this, both the 3' end of these things, like they both are complementary to each other. So rather than these primers going and annealing to the template strands, they themselves get annealed, and that stops my PCR reaction. At the same time, now the primers should not be self-complementary even, like very simple. Again, if a primer G C A T C G A A G C C T, this is the primer. If we design this, now this parts again like ATEC, this part and this part both are complementary. Then what happened? An hairpin loop gets started, and because of the complementary state stands both of them, they just get annealed themselves and form a hairpin loop over there, and that again prevents the binding of the template stand, and that again stops the reaction, right? So requirements of raw materials required. Primer designing is very important. Primer designing is very important for each reaction. So this is about the PCR requirements. And so next session we are going to see the detailed mechanism of the PCR reaction. So we'll select. So signing off for now, Sudhakar.